So here at Colorado State University, we have an engines lab. And in the engines lab, we have a Cummins 6.7 liter turbo diesel made by Cummins. It runs a binary that is proprietary to the Cummins engine company. And we actually work with Cummins. They're one of our partners. And we've created a synthetic vulnerability to help exercise the tools from the DARPA Assured Micropatching performers. One of those removes a check that is normally existent, and then when that check is gone, then the network can start filling up too much resources on that engine controller. When that happens, the engine controller can no longer control the engine. It will then start stalling. By exercising those commands, the engine actually has a physical effect. So when we're dealing with cyber physical systems, there is oftentimes a physical effect. So one of the nice things about this challenge problem is we can actually see and hear that when the engine starts stalling. The engine will go into a reset, turn back on again, and everything's fine, except if you keep iterating on this same, we'll call it an attack, like we're attacking the engine, then it stalls out. The patch, when it's applied correctly, will eliminate that behavior. It fixes that vulnerability, and the engine will just hum along normally, even though you're sending the same messages that used to cause it to stall. What the operators who are exercising the tools will do is they'll understand this binary using some of the decompilation and reverse engineering tools that are being developed. They'll know exactly why things happen at that point. And then when they apply the patch, it changes the behavior around that little region and makes sure that the execution of these parts that weren't behaving correctly before never happen again. And it's a permanent patch. It's a way that things will continuously be maintained and stay hardened against potential cyber vulnerabilities.